So graphs are the best way of understanding limits. Okay, if we can look at something and we can say that a limit exists, we can see it. We can actually see it. So, but we want to also have some formality to this. Okay, some limit formality. And the following criteria is what we're going to use then. So this is what we just talked about a little bit earlier, that the left-hand limit and the right-hand limit, sorry, this is a right-hand limit and left-hand limit, if they are the same, okay, and they're equal, then we say that a limit exists. Okay, that was the issue right here. The left-hand limit and the right-hand limit are the same, so then we say that the two-sided limit exists. If the left-hand limit and right-hand limits are not the same, we say the limit does not exist, or D and E. And that was the case here. Okay, we have the left-hand limit and the right-hand limits. Okay, they are different here and here. So we say that the limit does not exist. Okay, so the two-sided limit doesn't exist unless the right-hand and left-hand limits match. So let's state if the limit exists. Okay, we're approaching -4 from the positive side. So -4 from the positive side looks like this. Okay, so it looks like it's going down like this. Okay, so it looks like it exists at -infinity. Okay, and again, there are some books that say that because it's -infinity, it doesn't exist. But typically, we would say that this is going to a limit of -infinity. What about -2? Okay, and this is a positive, the one-sided limit, so that's okay because there's nothing on the other side. So if this was a two-sided limit, it wouldn't exist. What about as we approach -2? We're approaching -2 here. Actually, I should use a different color. We're approaching -2 here. Looks like it's approaching 2. And from the other side, it looks like it's something different. Okay, so because the two limits are pointing in different directions and to different places, we have to say as a two-sided limit, it does not exist. At x equals 0, okay, we can say that it's going to this point. Okay, in fact, it's continuous because there's a point there. So continuity has something to do with these limits existing. So as x goes to 0, it equals 1. Okay, now just because the limit exists doesn't mean it's continuous, because it could still be a hole. But if it equals 1 and the point exists at the limit, then we can say that it's continuous because we don't have to lift our pen to draw through that point. So this case is actually continuous. Okay, but again, the limits don't care what's happening at that point. It's just worried about what's happening as we get to that point. So this is the same issue here, except this is slightly different. So this is the same limit. The limits are exactly the same as going to 0. So left and right hand limits, okay, they're the same, just like we had up here. The left hand, right hand limits are exactly the same. So from the limit perspective, these are exactly the same question. Okay, it's equal to 0. The difference is this is discontinuous. So just because there's a limit, just both of these have a limit, this was continuous, this was discontinuous because there's a hole in there. Okay, there's a jump. Okay, so it's a jump discontinuity. So because of that, we can't say it's continuous. However, from the limit perspective, we do not differentiate between these two. Okay, because the limit again does not care what's happening at that point. So looking at these algebraic limits then, how do we deal with these? Well, if I talk about the limit going to this square root function, okay, 1.5 or 3 over 2 is going to give me 0. The problem is this implies that I'm approaching that coordinate from both sides. Okay, and the square root function, I'll just sketch it over here. Where's the place I can sketch? I'm going to sketch it over here. This square root function is going to be, there's our 3 over 2. It's not defined on this side of square root of 3 over 2. So this limit cannot exist, okay? Because as a two-sided limit, it cannot exist. However, as a one-sided limit, okay, this does exist. And exists and is pointing towards y equals 0. Okay, so this again is the issue of one-sided versus two-sided limit. This doesn't exist as a two-sided limit, but it does exist as a one-sided limit. So this log x function, as we approach 0, okay, again this is a problem because a log function, if we take a look at a log function, this is log x, it's only defined from one side of 0. So this implies that you're approaching 0 from both sides. Okay? So it does not exist. As log x approaches infinity, okay, this is easier because infinity by its nature is a one-sided limit, and although log x grows very slowly, it will eventually get to infinity. This last one here, it's not the last one, but the last one for this page, we have this function. Okay, I'm going to draw it here. This is going to be 2 over e to the x. It's actually an exponential decay graph. Okay, but what's happening as we approach 0? Okay, well, we actually have no problem because as we approach 0, it actually is, we can actually evaluate this value at 0. So this becomes our two-sided limit from this side and this side. There's no hole there. So we just plug it in. We go 2 over e to the 0. Well, that's equal to 2. Okay, so make sure that when we have limit notation, that if we can actually evaluate the limit, we actually just plug in and evaluate. It doesn't have to be some limits aren't used for these, difficult places. Sometimes they're just used to evaluate some points. Okay, but again, it doesn't tell us, the limit doesn't tell us exactly what's happening there, but we could use that point there to evaluate the limit.